Okay, we left off here last time, and let's continue on. So once we had developed this idea of quantum mechanics and electromagnetic radiation, now all of a sudden we can visualize where these electrons in the hydrogen spectrum are transitioning. And we have a series of things, and I'm not going to ask you to know these, but we have the Lyman series, the Balmer series, and the Paschon series. And these are different transitions, but I'm going to ask you to calculate various transitions. I'm not going to ask you to memorize these things. So we started out this lesson talking about glass tubes in a lighted signs, and they contain various noble gases or a mixture of these gases. Why do the colors of the light depend on the gases that are used? Well, they're basically a fingerprint. Each gas has its own characteristic emission spectrum, creating different colors of light when excited electrons return to the ground state. We can also change the amount of energy that we're giving them so that we can get only certain emissions from the lights. So, in the hydrogen series, which of the following transitions produce a spectral line of greatest energy? We have to remember a couple of things. Are the rungs the same spacing apart on that ladder in the very beginning we were discussing in section 2? And they are not. So even though all of these are 1, if I subtract those two numbers, it's 1. The greatest energy difference would be the one that has the lowest two numbers. So this answer is A. If I'm asking about an emission spectrum, it should also be from a higher energy level to a lower energy level. So if I had n equals 1 to n equals 2, that's not emission, is it? That would be absorption. How does the quantum mechanics differ from classical mechanics? Well, in classical mechanics, can't really describe how electrons are being transferred and how those emission spectrums are working. Given that light behaves as waves and particles, can particles of matter behave as waves? That's a good question, isn't it? And Louis de Broglie referred to the wave-like particles of matter as waves. His reasoning led him to a mathematical expression for the wavelength of a moving particle. Interesting. You're not going to have to know it, though. Today, the wave-like properties of beams of electrons are used in viewing objects that cannot be viewed with an optical microscope. So you used a microscope, hopefully last year, in biology, and that's an optical microscope. We have to use something like a scanning electron microscope to be able to look at atoms and very, very small details. So in this picture, we have electron microscope is used because it has a smaller wavelength, and so then we can get these pictures. And I think this is a pollen molecule grain, and we would not ever be able to see that with a traditional microscope. In classical mechanics adequately describes motions of bodies much larger than atoms, while quantum mechanics is used for very small particles and subatomic particles such as atoms and electrons. Heisenberg uncertainty principle states that it's impossible to know both the velocity and the position of a particle at the same time. And yes, you do need to know his uncertainty principle. This limitation is critical when we're dealing with really small particles like electrons, and that's because if it's an ordinary car or airplane, measuring its velocity is not going to change its position. But when I hit an electron with radiation, I can either see how fast it's going or I can see where it is positioned. I cannot determine both. So, to locate an electron, I'm going to strike it with a photon of energy, And as soon as I do that, I will move its position. And so I can either know one or the other. I cannot know both. Heisenberg's uncertainty principle states that it is impossible to simultaneously know which two attributes of a particle. And that would be velocity and position. Finally, we're at the end. This was a meaty section, wasn't it? When atoms absorb energy, their electrons move to higher energy levels. These electrons lose that energy and they emit light when they return to the lower energy level. To explain the photoelectric effect, Einstein, so you know photoelectric effect with Einstein, proposed that light could be described as quantas of energy that behave as if they were particles. The light emitted by an electron moving from a higher energy to a lower energy level has a frequency directly proportional to the energy change of the electron. Classical mechanics adequately describe motions of bodies much larger than atoms, while quantum mechanics is used to describe motions of subatomic particles and atoms as waves. Two equations you need to know: C equals h nu, E equals h nu, and you should also be able to calculate wavelengths changed from nanometers into meters. And that's 1 meter equals 1 times 10 to the negative 9th meters. Or 1 times 10 to the 9th nanometers equals 1 meter. Vocabulary in this section: amplitude, wavelength, frequency, hertz, which is 1 over seconds. Electromagnetic radiation, spectrum. Atomic emission spectrum is different than atomic absorption spectrum. Planck's constant, photoelectric effect, photon, ground state, Heisenberg uncertainty principle. The big idea of section 3 is atoms, the structure of atoms and their electrons, and that electrons can absorb energy to move from one energy level to a higher energy level, and when that electron moves back down to a lower energy level, it will emit that energy as light. We got to the end. I will see you in class. Bye.